The ability of an atom to attract electrons, its electronegativity, might be so strong that the atom does not share electrons with other atoms, but instead strips electrons away from other atoms. Chlorine has a high electronegativity, whereas sodium has a very low electronegativity. Because sodium has a low electronegativity, it holds its outer electron very loosely and easily loses it to chlorine. When this happens, chlorine fills its outer shell with 8 electrons, becoming negatively charged. Sodium loses its electron and becomes positively charged. Atoms that have lost or acquired electrons are called ions. Positive ions, cations, and negative ions, anions, form ionic bonds by an electrical attraction. In solid form, the ionic bonds between sodium and chloride ions are very strong because the ions are so close together. These ions make up table salt. Ionic bonds can be broken down in water. The partial charges on water molecules are attracted to the full ionic charges on the ions. When the solid dissolves, it breaks down into separate ions, each surrounded by a sphere of water molecules. The chemical reactivity of an atom is based on the number of electrons the atom contains in its outermost electron shell. Electron shells are depicted here as circles around the nuclei of the atoms. Each shell contains electrons with particular energy levels. Let's examine the electron shells of the element argon. The first electron shell holds just 2 electrons. These are electrons at the lowest energy level, the shell that electrons of an atom fill first. The next 2 shells can each hold 8 electrons. Argon's third and outermost shell is already filled to capacity, making this element extremely unreactive or inert. Chlorine also has electrons in 3 electron shells, but its third shell contains only 7 electrons. In chemical reactions, chlorine has a tendency to gain an electron, filling this shell with 8 electrons. This tendency to fill the outermost electron shell with 8 electrons is known as the octet rule. Sodium has electrons in 3 electron shells, but its outermost shell contains just 1 electron. Sodium cannot receive 7 additional electrons to complete this shell. This would require a huge amount of energy. Instead, sodium has a tendency to lose its outermost electron, leaving this atom with 2 filled inner shells. In general, elements with filled outer shells are inert, but atoms of all the other elements are chemically reactive and can form chemical bonds with other atoms. A chemical bond is an attractive force between atoms. Bond formation relies on the ability of atoms to share, donate, or receive electrons from other atoms. Let's examine the nature of a chemical bond using hydrogen atoms as examples. 2 atoms are depicted with their electron shells. 2 others are depicted more realistically, showing a region of space around the nucleus where the electron has a high probability of being found. This region is an electron's orbital. If 2 hydrogen atoms approach each other, the positively charged nucleus of one is attracted to the negatively charged electron of the other. The orbitals merge, and the electrons are then equally attracted to and shared by the 2 nuclei. The electron-rich region between the nuclei binds the atoms together. A covalent bond results when 2 atoms share electrons. In the case of 2 hydrogen atoms, each shares its single electron with the other. This sharing allows each to fill its electron shell with 2 electrons. The pair of shared electrons constitutes a covalent single bond. Let's now consider oxygen, an atom with 8 electrons. 2 electrons fill the innermost shell, and the other 6 electrons reside in the next shell. This outer shell needs 2 more electrons to complete it, the octet rule. 2 oxygen atoms form a covalent double bond by sharing 2 electron pairs from their outer shells. Carbon is perhaps the most versatile element on Earth, in large part because it contains only 4 electrons in a shell that can hold 8. To fill its outer shell, carbon forms 4 covalent bonds with up to 4 other atoms. In a molecule of methane, carbon shares electrons with hydrogen atoms, forming 4 covalent single bonds. Although this molecule is relatively simple, carbon often forms the backbone of large, complex molecules. With each carbon atom able to bond to 4 other atoms, carbon-based molecules are incredibly diverse. Triple bonds are rare, but nitrogen gas molecules, the most abundant molecule in the air we breathe, form triple bonds. The 2 nitrogen atoms share 3 pairs of electrons, allowing each to have 8 electrons in its outermost electron shell. In a covalent bond, 2 atoms may share electrons equally or unequally. In cases in which both atoms are of the same element, such as in molecular hydrogen or molecular oxygen, the electrons are shared equally by each atom. Sharing may be unequal between atoms of different elements, such as in the carbon and hydrogen atoms of ethane or the hydrogen and oxygen atoms of ethanol. For these molecules, we need to consider a concept called electronegativity, the ability of an atom to attract electrons. Oxygen has a high electronegativity, meaning that it strongly attracts electrons. Hydrogen has a much lower electronegativity. The shared electrons are drawn closer to the oxygen atom of ethanol. Because oxygen draws the negatively charged electrons closer to itself, it becomes slightly negative in charge, indicated by delta minus. Hydrogen, which doesn't hold the electrons as closely, becomes slightly positive in charge, indicated by delta plus. A covalent bond in which electrons are not equally shared is a polar covalent bond. Now let's examine the covalent bonds in ethane. All of the bonds are formed between carbon and hydrogen, which have similar low electronegativities and attract shared electrons nearly equally. No atom in ethane takes on a significant partial charge. The bonds between the atoms are nonpolar covalent bonds. The polar nature of the bond between oxygen and hydrogen in ethanol results in a polar molecule that can interact with other polar molecules. The hydrogen with a partial positive charge is attracted to an atom with a partial negative charge on another polar molecule, such as water. This kind of attraction is a hydrogen bond. The structures of many molecules, as well as their ability to dissolve in water, are based on the ability to form hydrogen bonds. A DNA molecule, for example, contains 2 strands of atoms. The bonds within each strand are covalent, but the 2 strands associate with each other through hydrogen bonds.